Yeah. So last time we talked about all the convex functions and its properties. Okay. And today we will just discuss a general formulation that connects machine learning with signal processing and many other applications. It's called the maximum likelihood estimation. So what happens is that in many applications we are dealing with a parametric family of distributions. It is denoted by P, X, Y. Okay. Well, Y is the observation. It's observed values, and X is the parameters, or it's the model parameters that we want to learn. And for example, this Y could be in binary classification. This Y could be the label of a patient. Right? 0 means healthy. 1 means the patient has a certain disease. Okay, you can take any seat. And this X is what we call the feature or the feature of the patient. Okay, we will see some examples later. And in many cases, we are looking at this maximum likelihood estimation. So we are looking for a variable X so that it maximizes the log of this likelihood. It's the log of this PXY. This is the probability of observing Y under X. And we want to max over X. Okay. This is a very general framework, and which turns out to cover many applications. Okay, so let's directly look at some of applications. The first one is related to signal processing. We have this linear measurement model, right? Well, this equation is a linear equation. Basically, the observation yi is given by the dot product between ai and x plus noise vi. Okay, let me write down this equation. So yi is, I use this notation for dot product. Okay. Well, ai and x are vectors. yi and vi are scalar values, and you can see they are compatible. This dot product is a scalar. This is the noise. Okay. For example, if you do MRI in medical applications, this is basically the equation, right? X is the underlying object. Maybe it's a part of your brain. AI is usually a Fourier transform, a Fourier vector, discrete Fourier vector. And this dot product meaning that we are doing we are measuring X at a certain frequency in the Fourier space, right? And this can be realized by using a machine, an MRI machine. And VI is the additive noise, thermal noise, or any other noise. And then YI is our observed observation from the machine. Okay, and we have a set of such measurements. So this I can range from 1 to m, let's say. Right? Maybe we are measuring the object at many different frequencies. So different AI corresponds to different measurements. Right? So in this equation, X is the vector of unknown parameters that we want to learn, we want to infer. VI is the IID noise. Okay, IID stands for identically independently distributed noise. Just for example, Gaussian. Okay. So we assume Vi, the noise follows a distribution with density Pz. If it's Gaussian, then Pz will follow a Gaussian distribution. And Yi is the measurement. Yi is the measurement. Well, Ai is the measurement vector. So what we have here is that we can here only the Vi is random. Okay? Only this noise is random. The other stuff are deterministic, and X is the unknown parameter that we want to infer. So we have Ai, we know Ai, and we know Yi. Okay, we know these two, and we want to infer, want to learn X. Right. I want to recover the object, for example, in the MRI scan. So what we do is to build this maximum likelihood test. Okay, so I'm going to look at what is the probability of observing what is the probability of observing Y given an underlying X. So if I write it out, it is the probability of, because Y here Y is a vector of all the observations. Okay, Y1, Y2, and the Ym. Right, we have m of these linear equations. So we have m observations, Y1 to Ym. So I'm looking at what is the probability of observing these observations. And because each of these equation is independent, right? Because all the Vi, all the noise are independent, and all the AIs are just different. So basically all these Yi's are independent. So they are equal to the product by independence. They are equal to the product of every observation. Right, by the independence in probability. Yeah. Of course, here you have to assume the noise are independent, okay, so that you can do this decomposition. If in practice, if for some reason the noise is not independent, then you will have to consider their dependence. That will make things more complicated. But this is usually what we assume and it holds for many applications, right? By independence, we can do that. Okay, now what is Yi? Yi is this. Let me see, what should I write here? Yeah, I should, okay. Yeah, here I should write V instead of Y, because only the noise part is random. V1, V2, and the Vm. And the Vi. Right. Think about that. If all the noise are fixed, then these equations will be fixed. Right. So all we need to consider, so the only randomness we need to consider is noise. So I'm going to look at, yeah, question.
And so at the top it says you're doing linear measurements with 2D noise, but the noise vector is only 1D.
Here, yeah, here Vi is a scalar. It's a scalar. Why? Because AI transpose X is a scalar. The dot product is a scalar. Right. This is a dot product between AI and X, gives a scalar. And Vi is the additive scalar noise. Right. So what Yi is a scalar observation. It's a scalar.
So AI is also noise?
AI is what we call the measurement vector. AI is not noise. So AI is a vector. We call it. We use AI to measure, to interact with the underlying object X. This is measurement vector.
So what's like a real world example of a measurement vector?
Yeah.
It'd be like the image coming out of a camera?
Yes. If you want to, in many scientific applications, X is like a real part, like object in the 3D or 2D space. AI is a light cast on the object, and there's on the far field there will be diffraction images. Okay, so this optics process is modeled by this linear equation. It's like casting a light on an object, and you can record some images or recordings on the far field. This is one example. Another example is that X is a part of the patient. It's like a brain or some part of the body. AI corresponds to a Fourier vector, discrete Fourier vector at a certain frequency. When you take the inner product, you are calculating the Fourier transform of the image at a certain frequency. Right. So this is how the MRI machine works. You are measuring these different physical objects at different frequencies, and then try to reconstruct them from the Fourier space. Right? All this can be modeled by these mathematical linear equations.
So the A vector, the measurement vector, would be like voltages you're getting from an MRI machine, depending on the position, right?
They are Fourier. I think they are Fourier vectors, meaning that for most of the time they are fixed. Like in the Fourier transform, we have the sine or cosine transformations, something like that, or complex Fourier transform vectors. Yeah. So they often have an analytical, like those you will know what those vectors are. Sometimes they are complicated vectors, but they are usually given.
Oh, so it's an inherent property of the machine.
Yes.
It's
Yes.
the AX.
Yeah. So when you measure this object at a certain frequency, you will be using a specific AI. Yeah. So that's why we assume AI and YI are known, right? We know the observations, and we know the measurement vectors. We use these AIs to measure the underlying object. And this measurement will be corrupted by a noise, VI, and so to give before we see the final observation, YI. So we just want to model this, the probability of this noise. Once we know the noise, all the YIs will be fixed. So, and by the independence of the noise, we can just decompose them. And moreover, these VIs, according to the equation, VI is just YI minus this dot product. Okay, just plug it in. Okay, so this is the likelihood of your observation. Okay, and following the maximum likelihood test, we want to look for X. We want to infer the underlying unknown parameters X, so that this likelihood is maximized. Okay, so that we have the maximum probability of seeing what we observe. And then now, because maximize a positive number, like this is a probability, so it's a positive number, is equal to maximize its log, the log of this number, right? Because log is a monotonically increasing function, right? So these two problems are equivalent. And why do we want to introduce log? You can see the px has a lot of product in it, right? That makes things complicated. So introducing a log can decompose these products or simplify these products. And yeah, this is just for convenience. Okay, and so after taking log, the product will become summation, right? So in the end, we end up with this maximum likelihood estimate. We want to maximize over x of such a maximum likelihood objective function, right? So after you take log of this one becomes sum of the log of each probabilities. Okay. So this is the maximum likelihood estimate. And you can see that this optimization problem depends on how we model the noise, P. P is the density of the noise, right? It's the P, the density evaluated at yi minus this dot product. This residual is basically your noise, right? This is the probability of your noise observation. Okay, so for example, if we assume the noise follows a Gaussian distribution, which in many cases we make this implicit assumption. So every VI follows from this Gaussian distribution, for example. And what is this Gaussian distribution? Well, this is the Gaussian distribution. This is the one-dimensional Gaussian distribution, PDF, right? With variance sigma. Okay. Now, given this one, we can plug this into the previous objective function. So we have PZ here. Replace PZ by P of yi minus AI transpose X. Yeah, just to replace this one. Replace Z by this scalar. And then plug it into this objective function. Take the log and take the sum. Eventually, the objective function can be simplified to this one. Okay. And we can see the first, so we are trying to maximize this objective function over x, right? You can see the first term has nothing to do with x, so it's going to be a constant. This is a constant, only depends on the variance of the noise, so we can ignore it. We only need to max over the second term, right? So maximize over the second term. Yeah, maximize over the second term is equivalent to minimize, because there's a negative sign here. It's equivalent to minimize over, right, the negative of this term. So we can get rid of the negative sign. And this is a problem that you may have seen in some of the application. This is called maximum likelihood, or this is called least square solution. Okay. And it's very natural. You just consider yi is your observation and AI is the corresponding measurement. You just consider their difference. You want to find an x that minimizes this difference, right? And so this difference will be called the error, and you raise it to the power of 2. Just, well, maybe it's a very natural choice because it's differentiable, nice. You raise it to the power of 2, and then sum up this error terms. Okay. You want to find an x that minimizes the sum of all the errors. right? So given yi and ai, you can find an x by solving this optimization problem. Okay. This is called LS, least square solution. And here we actually see what this least square originates from, right? It starts from that maximum likelihood model and assume the noise follows a Gaussian distribution, right? If the noise follows a Gaussian distribution, then it's kind of uniform in some sense. So the estimate, right, the test will become a least square solution. Okay. So whenever you see a least square problem, you can say that you are assuming the noise follows a Gaussian or Gaussian-like distribution. And another example, if you believe the noise is not Gaussian, right? Say it follows a Laplacian distribution, and this is the PDF of a Laplacian distribution. It's different. It's a kind of two-sided exponential function, but different from the Gaussian function, right? Gaussian PDF. You do the same thing. You plug in PZ into the previous objective function and simplify that, take the log, right? You can end up with this loss function. Again, the first term is constant, and second term matters, right? And if you compare the second term, you see a big difference. Now the second term is only looking at the absolute value of the difference, right? But on the Gaussian noise, we are looking at the square of the difference. These two are different, very different models, different problems. Yeah.
What's the difference between Gaussian noise and Laplacian noise, and what kind of phenomenon would cause each of them?
Yeah, if you compare their PDF, Gaussian has a faster decay because it's e to the power of negative z squared. But the Laplacian is e to the power of negative z, absolute value of z. Right? So they are these two distributions are, I would say Gaussian has a lighter tail, so it decays faster than Laplacian PDF. Right? So in this sense, it depends on how you model your the noise in your applications. If you believe your noise has there are some tests that you can use to decide if some noise follows Gaussian or Laplacian. Yeah, but these are two very different PDFs. They have very different statistical behavior. Okay? You can see from their PDF function, and consequently, this will also, you see, because of this square in this exponent, we end up with this square term in the loss function. And because of this absolute value in the Laplacian PDF, we end up with this absolute value, right? Because log will cancel out with this exponential, right? That gives us this absolute value. And then for the Laplacian, under the Laplacian noise model, the maximum likelihood test estimate is actually corresponding to an L1 norm solution. Right? If you still remember, this is kind of like the L1 norm of your noise.
So just to get a better visual understanding on this noise. So here's the Gaussian bell curve, not a very pretty one, but would the Gaussian noise be plotted over frequency? So certain frequencies have more noise. Is that what it means? Or what is Gaussian about the noise?
Yeah, the distribution is about this VI, right? This V. So what we're talking about the distribution of this noise VI, and VI is a scalar, one-dimensional random number, right? So if you believe VI follows Gaussian, then this would be the PDF of this V, right? This is V and this is the probability density of each realization. Right? This is the probability of V.
That makes sense.
Right.
Okay,
But
so the noise is the variation in where the value is going to land. So if there was no noise, everything would be the mean. Is that right?
yeah, the mean in this example, right, mean is 0. Right.
Okay.
If you assume there's no noise, then Vi is simply 0. All the Vi's will come back. All the Vi's will be 0. Yeah. So the noise, we usually put the noise in the model, right? Because in practice, there's always some variations in your measurement. Yeah. If Vi is following the Laplacian, then I believe it looks like this one. No. Yeah, it's a two-sided exponential function. So it's gonna be, I mean, they're kind of similar, but when the noise goes to infinity, they have this one decays faster than the Laplacian. So yeah, but in the end, we end up with two different optimization problems. This L1 norm solution is totally different from the least square solution. Later on, when we talk about the algorithms, we will see that we need to design different algorithms to solve it. Yeah. Another example is this logistic regression application where we talk about designing a more probabilistic model to do binary classification. Okay. So what is the problem set up here? We have a bunch of observations. This is our data. This is our data. UI, think about this. Every I corresponds to a patient, for example. UI is the some statistics that we collect from the patient. Could be the blood pressure, could be anything related to medical health, right? If you're talking about cancer, maybe UI denotes some features about cancer that you can collect from the patients. YI is the label, a binary label assigned to that patient, right? 0 means, for example, no cancer. 1 means has cancer. Okay, so this is a labeled data set, right? We are given features of patients, labels of patients, binary labels of patients. And we are trying to build a prediction model so that if you give me the features of a new patient, the model can predict the corresponding Y to do diagnosis. So what we can do what logistic regression does, right, is to model this YI using a probabilistic model. So this is how we model this YI. The probability of Y equals to 1, because it's a binary problem, right? So we just need to look at probability of Y equals to 1. The other case, Y equals to 0, is basically 1 minus this probability. So we can model what probability of Y equals to 1 in this way. It's a exponential A transpose U plus B divided by 1 plus this exponential. Well, A and B are the parameters that we need to learn. Okay, we need to learn these parameters. if you give me a data set, we need to learn this problem. So what this model does, you can think about, okay, suppose I solve a logistic regression problem and somehow I get a very good A and B. And how do I utilize this model? Well, say you have a new patient and the patient has feature vector U, right? What you do is to compute, take the inner product between A and U plus B, and then just calculate all this big fraction number. This number will give you, and you can tell it's between 0 and 1 because it's positive and the numerator is less than the denominator. Okay. This number will give you the probability of that patient having cancer. Right? Y equals to 1 means have cancer. Right? This is the probability of having cancer. If this is very high, then maybe the model is raising some concerns about this patient. Yeah, so that's how we apply this model, right? But here the question is, say if I give you a bunch of labeled data sets, how can we learn a proper A and B? So this is again, we can do this by following the maximum likelihood framework. So the problem is to learn A and B or estimate A and B from n observations. Okay, I give you n observations, n patients, features, labels, and we can build this log likelihood function. Okay, and here without loss of generality, we can rearrange these data sets so that here I assume the first K patients have label 1, the rest of the patients have label 0. Okay, but in practice you can always rearrange them. Doesn't matter, just for convenience. Okay. And this is basically in this big parenthesis. Okay, within this big parenthesis, this is the likelihood of observing this data set under this probabilistic model. Okay. Because if you look at the first product, I from 1 to K, for the first K patients, their label is 1. So because their label is 1, so each of the probability of the patient is just this fraction number, right? So we are just multiplying those probabilities together. And for the rest of the patient, this is from K plus 1 to M. For these patients, their label is 0. Their label is 0. And Y equals to 0, right? Because Y equals to 1 follows this distribution. So we can infer that Y equals to 0 follows this one. It's just 1 minus this one. Right, so this is the probability of Y equals to 0. Right? These patients, they have label 0. And this is the probability of observing zeros for those patients. And so multiply all them together is the probability of observing the entire data set, right? And then take the log. Take the log. And then you simplify this expression, you end up with this loss function. Okay, it's a times u plus a times ui plus b minus this log term. Okay. And this is a concave function in both a and b. Okay, you can check using the rules that we introduced before, right? The first term is a linear function in A and B. So the first term is linear. The second term, this part is convex. This part is convex. But because of this negative sign, so it is concave. concave in A and B, right? So it's a linear function and a concave function. So the entire function is concave in A and B, and we are trying to maximize this likelihood over A and B. Okay. So if you give me UI and yi, I just need to solve this problem, okay, for A and B over A and B, and then after that, I will have my model. Once I solve the problem, this is my this is the model, prediction model that I can use. And this is a convex optimization problem because we are maximizing over a concave function. This is equivalent to minimizing the negative of this function, which is convex. Okay. So you see, this is classification, and you can further extend this to this is a binary classification. You can extend it to multi-class classification. Right? This is one extension, and the other thing is that here we are talking about we use this logistic model to model this probability, but you can also use neural networks to give it more flexibility, right? So you just replace these exponentials by neural networks, and then it becomes a deep learning problem. So that is essentially deep learning. And again, similarly for this least square or L1 norm solution, this is for prediction. Yeah. So this example is right. This is a classification example, and this is an estimation example. In these examples, we are talking about linear models, right? So the yi, the observation is coming from a linear model, ai times x. But this depends on your application, right? If you are talking about a linear system, you use a linear model. But you can also model this using a neural network. You can replace this by a neural network. Okay, so this shows that through this maximum likelihood framework, many problems, right, can be connected through this framework, coming from signal processing, coming from statistics, and machine learning classification. They all follow this a unified framework, but we are just using different models and functions. And all these problems are convex optimization problems, right? That's why we want to talk about convex functions at the very beginning. Again, this is a convex function. Right? This is a quadratic function. Quadratic in X is a convex. And also, this is also convex. We have seen this before. Yeah, so I will skip that. Okay. So this is the lecture 0, and today we will start from lecture 1. Start to talk about algorithms for solving different types of problems. So from the title, you can see we are not talking about any specific problem. Okay? In this course, what we do is like we care about a class of problems, okay, that satisfies some abstract conditions. Okay. We will see many examples that falls into this class. And then for this class of problems, we are going to design some algorithms that can be, right? So we are not talking about any specific application or any specific problem. We are talking about a class of problems. And then we design algorithms to solve this entire any problems in that class. So the first lecture, we will be focusing on gradient methods for unconstrained smooth problems. We will define this class of problems later. And to solve these problems, the method will be the so-called gradient descent or gradient methods. So this is the outline. We will start from here we will start from a specific class of problem called quadratic minimization problems. You can imagine this is the class of problems with a quadratic type of objective function. And then we will generalize this to strongly convex, and then convex and smooth problems, and in the end non-convex. Okay, in the end non-convex problem. So the class is becoming bigger and bigger, and then the algorithms is the gradient descent algorithm. And this is the abstract optimization problem that we will focus in this lecture. Okay, we are going to minimize function fx over the variable x. Well, this x is unconstrained, right? There's no constraint on this x. X can be anything in this vector space. But here we assume that f is differentiable. Okay? It's differentiable. For example, in the logistic regression problem, right? A and B is our variable x, right? And this problem is differentiable because log is differentiable. This linear part is differentiable. Okay. And in these examples here, the least square is differentiable. The variable is x. This part is differentiable, it's quadratic differentiable. But this one is not, because it has absolute values. Absolute values, look at one-dimensional example. Absolute value is not differentiable at the origin point. Okay, so we will need some other techniques to deal with non-differentiable functions. But in this lecture, we consider that we focus on differentiable functions. And if you look at the goal, right? The goal is to find an x that minimizes f, which means we find an x that gives the lowest value attainable on f, right? So a very natural way to design algorithms is to follow this iterative process. We start from a initialization point x0. If you give me any initialization point x0, the algorithm, it is desired that the algorithm can construct a sequence of variables xt, so that in every iteration t, we are achieving a lower function value. Okay, so it's called, we're going down. Function value is going down over this sequence of variables. Because the goal, remember, the goal is to minimize the function over x, right? So this is, at least this is a reasonable approach. We start from some point and then go down. And then a very fundamental idea is to design the iterative process in the following way. So the next variable xt plus 1 is based on the previous variable xt. okay, plus some kind of updates. Okay, we call this updates. Well, this dt is the update direction. It's like the previous iteration is at xt, and I'm going towards the dt direction. Okay, and this eta t is a scalar that we call the step size. Okay, eta t controls how far we want to go along this dt direction. And we will need to specify this dt and the eta t in the algorithm, right? We need to know how to come up with a good direction, update direction. Yeah, and the gradient descent is one of the most important example of this type of algorithms. The update rule is given by this equation. Okay? The next step, xt plus 1, is the previous step minus the gradient. Okay. So xt plus 1 is xt minus eta t times the gradient at xt. Right. So what you do is this. At any step t, you compute that gradient. Suppose you know how to compute it. You compute this gradient, and then you can, after that, you can update this. You can follow this equation to get xt plus 1. And this is an illustrative example where you start from x0. This is the contours of a loss function, right? Once we go to the inner side, the loss function will be decreasing. Okay, you can imagine that this is a 3D function. And we start from here. Now the negative gradient is like following this direction. X0, the negative gradient is here. And we take a step size eta t. Then this is x1. And at x1, we follow the gradient again. So it's along this direction. Right, so we keep going at the x2. So you can see in this example, we can, once we follow the gradient, we can move closer to this minimum point. This is where the loss function achieves the minimum value. And this is called gradient descent. So we are following the gradient to decrease the function value. And this algorithm is very simple to implement. You just need to know how to compute the gradient. Okay? Either you can compute them analytically, so you can implement it using Python or MATLAB, or if the function you're talking about is very complicated, like deep neural networks, then there are some software packages that can compute the gradient automatically for you. And in this example, the descent direction is the negative gradient, right? Remember here, right? This is the abstract update rule we're talking about, right? So compare this one with the gradient descent. We know that the descent direction is negative gradient. Yeah, in fact, in many cases, you don't have to follow the negative gradient. You just need to follow any direction that has a positive correlation with this gradient. But I think I will just skip this part. So we just focus on this gradient descent update rule. Yeah. So let's look at the first class of problems. It's a very classic problem called quadratic optimization. So we are talking about minimizing this function. It's a quadratic function. 1/2 x minus x star times q times x minus x star. Again, every vector corresponds to a column vector. Right. So this x minus x star transpose is actually a row vector, a row times a matrix times a column vector. This fx is some scalar, right? So quadratic function, scalar values quadratic function. And here we require this q to be positive definite. Okay. We are talking about quadratic, this type of quadratic functions with a positive definite matrix q. Okay. Positive definite means that the eigenvalues are all or singular values are all positive. The gradient and for this function, gradient is given by q times x. Very similar to the one-dimensional derivative rule. Just q times x minus x star. Okay.
What was x star again?
Oh, x star, yeah. Actually, it is a given, just given constant. Right? But in this case, x star is actually the minimizer. Okay? Minimizer. Because once x reaches x star, this function is 0, right? But on the other hand, the function is non-negative because q is positive definite. So 0 is the minimum value of this function. This is just to make things easier. But in this case, we know the minimum, we know the solution is x star. But of course, in practice, we may deal with something like, it might be a just quadratic, and you have this linear and the terms, right? And let's say q is positive definite. So this is a strictly convex problem. So the minimum value is given by the gradient set to 0, right? The gradient is qx plus a set to 0. So x is just q negative q inverse a. Sorry, I think here should be a small a. It's not a matrix. Right. So if you're talking about a general quadratic function, but if we solve this problem in this way, right, it's going to be computation intensive because we need to compute q inverse. If the matrix is huge, computing the inverse is very, very, very slow, right? Very, very slow. So actually, we prefer to use iterative methods to solve this, to compute the inverse in these cases. This is another comment, right? For this one, we have the analytical solution, but it's just hard to compute numerically. Yeah.
So I just want to understand what a quadratic function is. So, I mean, what I learned in middle school was the quadratic function is f of x equals x squared. But how does that extrapolate to more variables?
Yeah, you can, if you explicitly write out this part in terms of the coordinates of x, you will see this term depends quadratically on the coordinates of x. That's why we call it quadratic function. So the function depends only depends up to each coordinate of this x, right? Raise it to the power of 2. You will see those quadratic terms. Like think about if q is diagonal, this is just the diagonal elements times each coordinate to the power of 2, right? So that is the quadratic function. It's just the if q, if q, let's say if q is q1 and q2, then this is just the q1 x1 square plus q2 x2 square, right? And this is a quadratic function of this, okay, what is x? X is x1, x2. Right. So we call this we can just extend this to high dimensions. So as long as the function depends quadratically, right, on the coordinates of these variables, then we call it quadratic functions. Yeah, but if you write it into a matrix vector form, it's pretty much similar, very similar to the scalar case, but we just need to pay attention to the matrix notations, matrix vector notations. Okay. So solving this problem is numerically hard, right? Here we consider even simplified problem just to simplify some of the expressions. It's just x minus x star times q times x minus x star. This is pretty much like, in the one-dimensional case, this is like just like x minus x star square. And we know the minimum, the minimizer is just x star. But if this is one dimensional, same for the multi-dimensional case. Okay. And for this function, we know the gradient is given by q times the vector x minus x star. So you can, once you have that, you can implement gradient descent to solve this problem. Okay. You just need to multiply the matrix by the vector every time. And okay, if we apply gradient descent to solve this problem with this step size, then we will have this convergence rate. Let's look at this one. If I choose this step size, but this step size is 2 over lambda 1 q plus lambda n q. This is the lambda 1, lambda n is the largest and the smallest eigenvalue of this positive definite matrix Q. Okay? Suppose you can compute them, and then you pick the step size following this rule. And then you using the gradient descent algorithm, right? Gradient descent meaning that, let me write down the gradient descent. It's xt plus 1 right? And in this case, eta t is given by this one. Eta t is given by this one, and this gradient is given by this one, right? Gradient is given by this one. Okay. If you follow this gradient descent algorithm, right, you start from x0. Now you can do this iteratively, compute xt's along the way. Follow this algorithm, we can prove this result. What is this result about? It says that the distance between xt and x star, right? This is where you achieve at t's step. This distance is controlled by, is bounded less than or equal to, is controlled by the initial distance. Initial distance is your initialization and this x star, right? is controlled by the initial distance multiplied by this coefficient. And this coefficient is smaller than 1 because the numerator is the difference, but the denominator is the addition of these two. Right? It's something smaller than 1 to the power of t. Right? So you can imagine if I follow this process, and as t increases, when I run these algorithms for many t, and this distance will goes to 0 because this coefficient, this big coefficient, decays to 0 exponentially fast. Right? It's something smaller than 1 to the power of t. Then it will diminish to 0 exponentially fast. Okay. So this is the theoretical convergence guarantee for this gradient descent algorithm applied to solve these quadratic functions with positive definite matrix Q. Right. We will prove this very soon, right next. And we can see that, first of all, it converges very fast. Converges very fast. Imagine that inside, for example, it is 1/2, then 1/2 to the power of t, right? If you run t for 100 iterations, 1/2 to the power of 100, that is a very small number, right? That means at that time, your xt will be very, very close to f star. So this is the convergence guarantee of this algorithm.
What was lambda? Sorry if I missed that.
Yeah, lambda 1 and the lambda n is the largest and the smallest eigenvalue of this matrix. Yeah, and we can see that this convergence rate critically depends on this fraction number. Right? If this number is very small, then the rate is faster. Right? And this rational number depends on what? You can divide both sides by lambda n. So it depends on this ratio between lambda 1 and lambda n. We call this the condition number of this matrix. Right? Lambda 1 is the biggest, the largest eigenvalue. Lambda n is the smallest one. Ideally, it will be better if this is closer to 1. Condition number. So it's when we talk about a matrix, maybe the most important thing is either the eigenvalue, if it's symmetric, or the singular value, right? And for these values, one of the most important statistics is this condition number with the ratio between the biggest one and the smallest one. Yeah, we call this convergence geometric convergence or linear convergence. Right? Geometric means that something to the power of t, right? This decays geometrically or linearly. Yeah. And we have some time. Let's go through the proof. Okay. Let's go through the proof. So the way we analyze this algorithm is just to follow the update rule, right? I want to understand xt plus 1 minus x star, okay? And I know that the gradient descent, for the gradient descent, xt plus 1 is xt minus the gradient, minus eta t times the gradient, right? So this is I just plug in the update rule of gradient descent. And then what is this gradient term? In this example, the gradient is q times xt minus x star, right? So you can combine them together to get this matrix vector equation. So let me just write. Okay, maybe at this point, I can just write eta t. Now the gradient for this quadratic example is q times xt minus x star. Gradient f xt is just this term. Okay, and then you can combine these two. These two are the common factors, so you can combine them together. This I stands for the identity matrix. Just write them together into a matrix form. So what you see, this is a very interesting iterative process. The difference between xt plus 1 minus x star is a matrix times your previous difference. Right? This matrix is this is the matrix that we are talking about. This matrix times the previous difference. Right? It's kind of like a linear transformation. Right? Every time your distance is subject to such a linear transformation, if we can know some properties of these matrices, then maybe we can control the norm of this distance. Okay, now we take L2 norm. Now this is equality, right? This vector equals this vector. So I can evaluate the L2 norm on both sides. On the left-hand side, I can get the L2 norm. And this L2 norm equals to the L2 norm of the right-hand side, right? So we have xt plus 1 minus x star, the length, L2 norm, right? L2 length, L2 norm of this vector equals to the right-hand side. Okay, this is the, right? Because this is a matrix, this is a vector. So matrix vector gives you a vector. Multiplication, right, gives you a vector. And I can evaluate the L2 norm of that vector. Okay, and then following the matrix vector inequality, right? This is a side note. A times x, right, L2 norm less than equal to A times L2 norm of x. Right, matrix equal. Well, this A is the we call it many different names, but we call it the spectral norm or the operator norm of this matrix. But basically, it's the largest singular value. So this is like the linear transformation applied to this vector, right? And then after that, we evaluate its length. And this apparently the linear transformation will affect the length in such a high dimensional space, right? And this inequality is just a very coarse upper estimate of such an effect. Like in the worst case, this will be the upper limit of this the length. It will be your previous length multiplied by the largest singular value of this linear transformation. That is like the along that direction. This linear transformation will stretch the vector the most. Okay, along the largest singular value direction. So this is a fundamental matrix vector inequality. Right? It's just linear algebra. Okay, you need to remember it. And then all we have to do is see, we have now built a relation between the distance in t plus 1 and the distance in time t. We just need to understand this coefficient, this spectral norm of this linear transformation, right? This is a fundamental quantity depending on Q and your step size. It only depending on algorithm step size and their problem matrix Q. Okay. So the rest of the stuff is to analyze this quantity. Okay. In this case, mathematically we can show that the largest singular value of that matrix equals to this two. Okay. It's the maximum of these two. Maximum between 1 minus eta t times the largest eigenvalue and 1 minus eta t times the smallest eigenvalue. Because it's not clear which one of them has the biggest number. So if we take the maximum of these two. And you can further optimize that because it's the maximum of these two, and the eta t is the step size that you need to determine. So what you can do is to choose the eta t so that minimizes this entire term. Okay, you want to minimize this entire term. Why? Because if this term is smaller, it will make the distance smaller, right? You want to minimize this coefficient as much as possible, right? And this coefficient equals to this guy. Now what you do is to look for eta t that minimizes this, and turns out that okay, this would be the eta t that you're looking for. It's 2 over sum of these two. Now you plug it into this 2, I think they will be equivalent. Yeah, but in the end, once you plug in the entire spectrum norm, it equals to this one. Okay, this is a very classical result. Okay. So this one will be less than or equal to lambda 1 minus lambda n and lambda 1 plus lambda n. Okay, and then you can apply this recursion recursively over T to get this claim, right? So the next difference is the previous difference times this scalar. And you apply this to the previous one again. So it's this one to the power of 2 times xt minus 1 minus x star, right? And you just keep unrolling the recursion up to the initialization. So you will get the results. Okay, once if you unroll it t times, right, you can get this result. So you unroll it until you get to the initialization point. And this analysis is very simple, but it gives us some understanding of this algorithm and functions, right? So we need to utilize. So first of all, the first thing that matters is the algorithm form. Right here, we are specifically using the gradient descent. So the update rule determines this recursion. And the second thing is your problem. Because this is a quadratic problem with a positive definite matrix Q. And because Q is positive definite, we can have this nice properties. We can compute these singular values explicitly. So depends on both.
So I'm still a little bit confused on how the eigenvalues are incorporated into this. Like, why are we multiplying these two eigenvalues by Q? What do lambda and lambda 1 represent in a more comprehensible term for me?
Yeah, I think yeah, I think this value this value basically says, let's say, what does for a matrix, what does this operator norm mean? It simply means I consider any. It simply means I multiply this matrix by any vector that has a unit length. Now the question is, what is the, among all the vectors that has unit length, what is the maximum, what is the longest vector that I can get after applying this linear transformation? Okay. But if you find that that direction, that x is the direction where this linear transformation has the most strongest effect. You are stretching the vector in the strongest way, right? So that is called the biggest, the largest singular value. So along that direction, your vector can get amplified the most, right? And you will have the largest eigen singular value, the second largest singular value itself. Yeah.
Makes a little bit of sense.
Maybe we can have some more discussions next time. Yeah, about these eigenvalues and singular values. It's basically how we view this matrix in a standard basis, right? So, yeah, maybe next time I can give a brief discussion on this. Okay. Maybe we can discuss offline if you want. Yeah. So let's just end the class today, and yeah, next time we'll try to talk about strongly convex and smooth problems. Well, this extends this quadratic problems. Right? This is a quadratic problem, strongly convex and smooth problems. It's bigger. It's a bigger class of problems, but the analysis follows a similar spirit. So we will see it next time. Okay, I will see you guys on Thursday.
You hear me?
Yes.
Excuse me, where was the classroom? Because I wanted to find room 31, 33, but I mean, it was locked.
Okay. Yeah, we are in the classroom. So there are two doors to this classroom, right? Maybe, yeah, either you can knock the door next time.
Oh,
yeah,
okay.
or yeah, if you get in from the other side, that door should be open.
Actually, I tried both of them. They were both closed, so I just
Oh, okay.
yeah. I was
Yeah, maybe next time you just knock at the door.
okay. Thank you so much.
Yeah, I'm sorry that causes this inconvenience.
Oh, it's okay. I was online on Zoom.
Okay.
Thank
So
you.
yeah, see you on Thursday.